Kia ora, this video is for Ramika and Leo. So Ramika wanted me to do 3C and 3D, and Leo wanted 3D done. This is from this year's complex numbers paper. So question 3C is kind of a classic where we're given an equation and we have to solve it. And if we work in polar form using de Moivre's theorem, it's pretty straightforward. The key idea in here is that we can rewrite this equation to be z cubed is equal to negative k to the power of 6i, and k is a real constant. And if you think about what we've got going on here, if we draw this out, if k is a positive number, which we can hand wave and assume that it is, then it's negative, like it might be negative 8i, right? So we're down here. And this is the key to getting this problem right, is to think about what is that angle here in the original equation setup. But the other thing going on in here is that if we're solving a problem like, I'm going to do a simpler one, suppose I've got z cubed is equal to 8. I can write that as 8 cis 0, right? And I can draw that angle out here. But that angle of 0 is not unique. I could also write it as 8 cis 2 pi, right? So it's this idea of spins, and I've done some other teaching videos on this. So if you're not confident with this, if you're watching this video in 2023, and you're just learning how to do these, make sure you get really good at them because they come up all the time. Okay, so that's the first part of the setup on this one, just about done. And that means that I can rewrite this as, well, we're going to go z cubed is equal to k to the power of 6 times cis of negative pi on 2 plus 2n pi. Right, so now what I've done is I've dealt with the right-hand side, but I'm not completely finished dealing with the z cubed. So we're going to say that z, which is the thing I'm after, let z equal r cis theta. So on the left-hand side, I've got r cis theta cubed is equal to k to the power of 6 times cis of negative pi on 2 plus 2n pi. So you're probably going, some of you might be going, what happened to the negative sign in here? I've dealt with it by saying that I'm down here, so my angle is a negative pi on 2. Right? Using de Moivre's theorem, we can do some work on this side, and we get r cubed cis 3 theta is equal to k to the 6th times cis of negative pi on 2 plus 2n pi. Now all I have left to do is to match everything up. So r cubed is equal to k to the power of 6, which means that r must equal k squared. So that's the first part done. And now I have to figure out what theta is. Well, we know that 3 theta is equal to negative pi on 2 plus 2n pi. So theta is equal to negative pi on 6 plus 2n pi on 3. Now, this bit here makes sense because I know I've got a cubic, so I'm going to get 3 solutions, and this is saying that the angle is evenly spaced out at 120 degree things. Now, I'm going to try and draw 120 degrees, and I know that I'm going to muck it up, but it's going to look basically like that. Let's see, how are we getting on? Down there. Okay, close enough. So, putting all of that together, what do we get? Well, our first solution is z1 is equal to k squared cis of negative pi on 6. Right, that's substituting in n is equal to 0. The second solution is going to come when I substitute in n equals 1. So it's going to be cis of negative pi on 6 plus 4 pi on 6, working with this, which is k squared cis of 3 pi on 6, which is pi on 2. And the third solution I'm going to get, I'm going to substitute in n equals negative 1, and I get k squared cis of negative pi on 6 minus 4 pi on 6, which gives me k squared cis negative 5 pi on 6. Okay, the thing that I like about doing it with the n equals 0, n equals 1 and n equals negative 1 is that my angles in here, my arguments, end up being between negative pi and pi. And we like that. It's a convention that we've got that we use the principal value. So from 0 around to pi and from 0 back around to negative pi. Now, I think when the mark schedule comes out, you'll find that it doesn't matter if you've got negative pi on 6, negative 5 pi on 6 here, that you could also add on 2 pi. So it's probably going to be fine if you have k squared cis of 7 pi on 6. So there you go. Sorry about the background noise, guys. One of my kids has just decided to boil the jug. So hopefully that's fine. They live here too. So hopefully you can hear through the noise. So Ramika, that's the first question done. Let me know if that helps. Now the second one for Leo, I'm going to do in the same video. And that's to prove that there's no complex number such that this thing here holds up. And I've done this using a proof by contradiction. Right, and that's a slightly, it's a cool form of proof. We don't see it come up that often in level 3. What we're going to do is assume that there is such a complex number and then show that that can't possibly be true. Sorry, that can't be true. All right, let's just get some space. So as usual, when we start a proofy kind of complex numbers question, we're going to start by assuming what z is. So we say let z equal a plus ib. And for this to be a complex number, both a and b are going to be real numbers, and a and b are not equal to 0, right? Because if, well, we could probably have one of them be equal to 0, but if they're both equal to 0, the complex number is 0 plus 0i. I'm thinking about it. You know, we don't actually have to write that out. That's just going to make life more complicated than it needs to be. So assume that z exists. So that means that we must have the modulus of a plus ib minus a plus ib is equal to I. We're going to work this through to its conclusion and show that it doesn't make any sense. So the modulus of that is a squared plus b squared minus a minus ib equals I. I'm going to solve this, and I'm trying to find values of a and b that fit. So we get the square root of a squared plus b squared is equal to a plus bi plus I, and now we group the real and the imaginary parts like that. Now the next thing to do when I've got a surd equation is to square both sides. So we have a squared plus b squared, and here we have this squared. Now squaring that gives me a squared. I squared is -1, so it's going to be I squared minus b plus 1 squared. Leo, if this is a bit too fast, let me know and I can add some stuff into the comments, but hopefully this will be fine. And then the last bit is the combo bit with the a and the b plus 1i, so it's going to be plus 2a times b plus 1i. Right, so all I'm doing here is just expanding that quadratic. Okay, so we've got a squared plus b squared is equal to all of that. Now, I can subtract a squared from both sides, and now I can expand stuff out. We have b squared is equal to negative b squared plus 2b plus 1 plus 2a times b plus 1i. So you can see we're getting somewhere. Hopefully we're getting to a condition that isn't going to make much sense. Equating the real bits, we've got b squared, what have we got? B squared plus b squared. So what I'm doing here, guys, is I'm getting everything over to this side. Right, so b squared plus 2b plus 1 minus 2a times b plus 1i is equal to 0 plus 0i. Okay, so I'm collecting everything up together, and I'm looking at the real bit, and I'm looking at the imaginary bit. So what do we have now? Well, we know that if this complex number exists, then 2b squared plus 2b plus 1 has to equal 0, and then this bit here has to equal 0, so we get negative 2a times b plus 1 has to equal 0. I'm going to work with this first, and I'm going to find a value for b. right? And remember when we started out, we said that z is a complex number and it's a plus ib, and so that means that a and b are just ordinary real numbers. So we're actually just about finished here, even though it probably feels like we've got a way to go. I'm going to try and solve this, and I'm interested in whether I end up getting a real number for b. So different ways you can solve it. I know some of you are going to chuck that in your calculator. I'd prefer it if you didn't, since you're doing an algebra exam, but there you go. So we've got that. You can either do completing the square, which is what I'm going to do, or you can do quadratic formula. So in here we get b plus a half squared, take out the quarter that you added in by mistake and add the half. Here we get b plus a half squared is equal to, so here I've got positive 1/4, so I've got negative 1/4 here. And you can see now, hopefully, where this is going, that we've got b plus a half is equal to plus or minus the square root of this, which is 1/2 of I. So we've got a solution for b, but b is equal to, I just realised I've got a tiny mistake in my worked solutions I've put up for my own class, but never mind. So b is equal to negative a half plus or minus 1/2 I. Right, so here we are, we've got our contradiction. So we assumed that a and b were real numbers, but b is complex, right? It's unambiguously complex. It's got a half I stuck on the end, right? Think about where it is on your Argonne diagram. It's either plus a half I or it's minus a half I, but it's not 0. So b is complex. Therefore, we have a contradiction. Therefore, no such z exists, and we're done. Now there's another way we can do it, right? So here what I did is I started working with equating this to 0, but I could also have started working with equating this to 0. Now I looked at that. I think it's a little bit more work, but it's basically the same idea. So matching the imaginary parts, we get negative 2a times b plus 1 is equal to 0. So either a is equal to 0 or b is equal to negative 1, right? And now we're going to take each of these. So if b is equal to negative 1, we're going to say what's a? If b is equal to negative 1, then let's go back to over here. We have to have that this condition holds, right? So we found a value of b in here that will make the imaginary part 0, but we don't think it's going to work for this, and we're going to show that now. If b is equal to negative 1, then what is 2b squared plus 2b plus 1? Well, that's equal to 2 minus 2 plus 1. It's not equal to 0. So that tells me that b is not equal to negative 1. What about if a is equal to 0? Well, if a is equal to 0, then let's go all the way back to the start. Now, guys, I'm thinking about this. I think this might actually have been the excellence question, because I think this is worse than the one there wasn't in part E. So maybe there were 2 excellence questions. Okay, let's go all the way back to here and look at what happens if we assume that a is equal to 0. Right, if a is equal to 0, then we get on the left-hand side the square root of b squared minus bi has to equal b minus bi. So that is equal to b minus bi. Where am I going here? Anyway, so that's not equal to I. I haven't explained that well at all. Hang on a sec, let me do it again. Right, okay, so we're going back to here. So we're saying that if a is equal to 0, what does that mean? Go all the way back to the start. So if a is equal to 0, what do we have here? Well, we've got ib minus ib is equal to I. So this is just the square root of b squared, which is b, minus bi. which is equal to b minus bi, which is, what is wrong with my brain, is equal to b